So, Stefan, you can, please.
Okay, so just a moment. Okay, so can I start?
Yes.
So we will continue in that direction I promised on the last meeting, that we will investigate a little bit the coherent closure. So let's repeat what was on the last lecture. So a coherent algebra, or a subspace of a matrix algebra, is called a coherent algebra if and only if it contains the identity matrix, the all-one matrix. The algebra is closed with respect to operations of usual matrix multiplication, the Schur-Hadamard multiplication, and it is closed under conjugate transposition if we are working over complex field, and usual transposition when real numbers or its substructures. And what was important, that if we have inclusion between two coherent algebras, then what is under the second is called a coherent subalgebra. And if we have two coherent algebras of the same order, then their intersection is also a coherent algebra. So now it is interesting to ask, if we are given a matrix, what is the smallest coherent algebra that contains this given matrix? And as the intersection of all coherent algebras which contain these matrix, then this thing is well defined. Just we can think about this, that a coherent algebra containing a matrix M is also containing the matrices I and J, or I and J minus I. So these coherent algebras of rank 2 are the same, and they are contained in all coherent algebras which are containing the matrix M. So really this intersection is non-empty, and it is well defined. So there exists such a structure. And similarly, if we are given a set of matrices A1 up to AK, then similarly one can ask what is the smallest coherent algebra which contains all these matrices. And we are using notation these double brackets, or how to say it in English. So clearly, if these matrices form a standard basis of a coherent algebra, then the coherent closure is coinciding with this coherent algebra. So that's what we already know. And let us start with an example. And here we will use the Schur-Wieland principle, which we already had, I think, 2 weeks ago. So let us consider a graph K13 and its adjacency matrix. Now, we can also identify the adjacency matrix with the graph in some sense that, for example, if we will look for a coherent closure of a graph, then of course we will mean by this that we are looking for the coherent closure of its adjacency matrix. So maybe if I will say at some moment that coherent closure of a graph, I will implicitly mean that it is a coherent closure of its adjacency matrix. So let us take this graph and its adjacency matrix, and we are asking what is the smallest coherent algebra that contains this matrix A. So from the theory, we already know that such an algebra contains this matrix A, and also it should contain the identity matrix and the all-one matrix. Now, since it is a linear space, clearly, it has to contain also the adjacency matrix of the complementary graph or linear combination with this coefficient of the matrices which we know about that they are contained in the coherent algebra. So we are obtaining another matrix which lives inside this coherent algebra. So we at this moment know that A is there, A bar is there, the identity matrix is there. So in some sense, we obtained decomposition into 0-1 matrices of the all-one matrix. So it is natural to ask whether these three matrices already generate or algebra or not. So clearly, if the answer is yes, then A square, A bar square, or A times A bar, or A bar times A are all living in the same algebras. That means that it's easy, we have to check that all these matrices can be written as a linear combination of the matrices from the basis. So that's, for example, why we are checking what is the second power of the matrix A. If we count it, and also if we count A bar square, then we can clearly see that A square cannot be written as a linear combination of A bar, and I. And also A bar square also cannot be written. So we somehow has to refine our matrices or what we intend to obtain as a base, and we can do it by the Schur-Wieland principle. For example, from this matrix is clear that since it contains number 3 just on one position, then this matrix which has 1 on the same position and 0 elsewhere should be in the set of new matrices, I will say. So, and similarly here we have 2, so the matrix I is now decomposed into 2 matrices B1 and B2. This is by Schur-Wieland principle. So now we has to check with the new set of matrices. Again, their sum is the all one matrix, so it gives sense that we will check whether this set of 4 matrices generate the coherent closure or whether they are closed under matrix multiplication. So we will do the same job. Again, a few of the products will be expressible as linear combinations of the given matrices, but if we will count B1, B3, that is now A is called B3, we will see that the original matrix A is decomposed into matrices which will be later on called C4 and C3 and C4. So A was 0, 1, 1, 1, 1, 1, 1, and zeros, but since these two products has to be linear combinations of basic matrices, then we have to write A into 2 pieces. So step by step, we are figuring out whether the given set of matrix forms a basis, or if not, then what has to be decomposed into smaller pieces. So if we finish this job with checking the previous step, then we obtain 5 matrices. And now, if we will check step by step whether this set is closed under matrix multiplication, then we will see that yes, it is closed. For example, C1 times C1 is C1, C1 times C2 is 0, all 0 matrix, C1 times C3 is C3, C1 times C4 and C1 times C5 are 0 matrices, and so on. And as it is shown in this table, each product can be written as a linear combination of the matrices C1 up to C5. Is this clear, or should I repeat something?
Well, I think it's clear.
Okay, but because this is important and
Right, yeah.
principle, so I don't want to go so fast through this.
But what is a general algorithm to understand that this set is a generating set of this coherent algebra?
What is the general principle?
Yes, here there is a very nice example. There you can take good matrices and using some intuition, try to understand that really these matrices form a good basis for this algebra. But in the general case possible, it can be some probabilistic algorithm to test.
The general principle is that step by step we are doing that. We are refining the set of matrices. We know that the coherent algebra has a basis from 0-1 matrices. So that's why we are playing just with 0-1 matrices, which are summing up into the all-one matrix. And in each step, I am getting knowledge whether this set which I have actually is good or not. If not, then clearly I can, by the Schur-Wieland principle, some of the metrics replace with some set of matrices.
But possible, I'm asking possible about some effective algorithms. I mean,
okay, you are now asking for aspect from computer science.
Yes,
Aspect
sure.
whether from time complexity or so. This is subject of computer science. I know about this not so much, but this algorithm is, I think, polynomial of power 6 or something like this.
But this algorithm is probabilistic, am I correct?
Not probabilistic. You have exact algorithm, so you are not relying on randomness.
But I'm not sure in complexity of the exact algorithm, since possible you need to go through a rather long chain of steps, and I'm not sure in its complexity. But possible if in some step, if you take a random matrix from, for example, from algebra and try to understand is this matrix linear dependent or independent with our previous matrices. Possible after some step with some probability you can conclude that you need to take stop if this matrix is linear dependence, if there is a linear dependence.
I cannot understand why I should take a matrix randomly if I am finding a concrete, if I'm looking for a concrete coherent algebra. So.
Sorry, possible is better to continue in partial communication. Sorry.
Yes, I think so, because now I have to confess that I am missing your point. So we have to understand that this procedure clearly gives us a coherent algebra which is closed under usual matrix multiplication, and also since we are choosing the basic set of matrices in order to have this disjoint support, that meaning that if two matrices are different, then on the place in which one has 1, then the second will have 0 on the same place. So they will have disjoint support, and we have to check that this set is really closed under conjugate transposition. Also, we have to check that we can express the all-one matrix using these matrices from the basis, and also we can check that the identity matrix can be written as a sum of some matrices from the basis. So really, we are having a coherent algebra, and by the construction, it is clear that we constructed the minimal such coherent algebra. So this, how does it look like on a concrete example? And a combinatorial interpretation of the matrix multiplication is used to obtain the so-called Weisfeiler. I have a misprint. So this is Weisfeiler stabilization in order to find the coherent closure or WL closure of a graph. So this algorithm comes from the motivation to find an efficient algorithm for solving the graph isomorphism problem. And these days or these years, it is very popular, and lots of generalizations are appearing, or lots of attempts to generalize it. So what does this algorithm do? Again, it is probably better to explain it on a picture. So let us start from a graph, and we would like to know the smallest coherent algebra which contains its adjacency matrix. So clearly, at first step, we can distinguish pairs of vertices in such manner that one set of pairs will be formed by the pairs which are joined by an edge. Another set of pairs will be formed by the set of pairs which are not joined by an edge, and a third set will be formed by the diagonal relation, that is, each vertex will be in relation with itself. So clearly, at first step, we can create three such sets or relations, and we can create the generalized adjacency matrix to this structure, to this so-called complete colored graph. So here in my notation, or in this matrix, the entry 0 corresponds to the green color, entry 1 corresponds to the black color, and red is color 2. Now, the formal procedure goes like this. Replace each entry with a variable, and with the same variable to the pairs which are in the same relation, and these variables are not non-commuting. So, for example, AB will be different from BA. And create the second power of the corresponding matrix. So here, to entry 0, the variable A is assigned, C is assigned to variable 2, or to color 2, and B is to color 1. And now we compute the second power of this matrix. So For example, if we count what is the product of the first row with the first column, we obtain a square plus 2b square plus c square, because I think the reason is clear to everybody, and so on. Step by step, we obtain a new matrix of size 4 by 4. And after that, we are assigning new colors to entries. For example, let's start to check step by step what entries are contained in this new matrix. So I can see that there is a square plus 2b square plus c square. So this will be my new color 1. After that, I find a new entry. This will be color 2. Going step by step further, this will be the third color, and finding out that this I already has, so this is a new color. We have to realize that since the second power of a matrix corresponds to the volts of oriented volts of length 2, that this is the same as to ask that if I have, for example, here such an edge, then how many of volts of length 2 with corresponding pairs of colors we have between two concrete vertices. So if for two pairs UV the corresponding numbers are different, then this matrix will assign them different colors. And if I cannot distinguish by this combinatorial interpretation some of such ordered pairs, then they will obtain the same color. So this procedure is simply just playing with the volts of length 2 and assigning new colors to pairs which are by this distinguishable. So here in the first step, I need 6 colors. And I will repeat the full procedure. So now I am going to count m times by m, m2 by m2, and step by step again to compute honestly the entries of the resulting matrix. And I will see that again, what is on the first place appears somewhere else here and in no other places, and so on. And I will see that here I do not need any new color. So if I compare this matrix with this, then I will see that the number of colors is the same, and those entries which were colored by the same color in the matrix M2 are also colored by the same color in M3. And exactly this is the state I have to reach. This is called that these two matrices M2 and M3 are equivalent. So, and the procedure is stable. So in the last step, in fact, I didn't get any new information. Besides that I reached the state that it is stable, the algorithm. So if this happens, then, as I said, we are called the matrices equivalent. And if we have in 2 consecutive steps equivalent matrices, that we reach the end of this algorithm, and we can now interpret the result. For example, in our graph, it was clear by simply the knowledge of the automorphism group that we will have 6 2 orbits. Just to, what was the labeling of this graph? Okay, I'm sorry. So this was 2, this was 1, 3, and 4. If we consider the group of automorphism, then clearly it is generated by these 2 elements, these 2 permutations. So one can say that it is isomorphic to Z2 cross Z2. And from this, if we have this information, then we know that the number of 2 orbits will be at least 6. Or we know that the number of 2 orbits is precisely 6. But it says that by the stabilization, we will reach at least 6 orbits, because those relations which are distinguishable by the group of automorphism, they will be clearly colored differently in this procedure. But during the procedure, we obtain that 6 colors are enough. So this means that the stabilization found exactly the 2 orbits of the full group of automorphism. And on the other hand, we can obtain the original graph as a union of some of the 2 orbits. So this is another, I would say, byproduct of the stabilization, that it breaks the full graph into such pieces, or that we are able to construct it as a union of suitable 2 orbits of the full group of automorphism. So this is how the WL stabilization works. I don't know, should I repeat something, or was it clear? Maybe I will make a remark that in some sense this algorithm is a generalization of the concept which works in 1 dimension naturally. That, for example, if you would like to distinguish just the vertices, then of course in the first step you will say that I will distinguish the vertices according to the degrees. So here you have degree 2, here you have degree 2, here you have degree 2, here you have degree 3, here you have degree 3. Fine. So in the first step, you obtain two colors. And in the next step, you can write to each vertex how many neighbors of color of yellow color and how many of green color it has. So for example, this vertex has 0 yellow neighbors and 2 green neighbors. This one has 2 yellow, 1 green. This has also 2 yellow, 1 green. This has 1 and 1. This has 1 and 1. And now you can distinguish 3 types of vertices. So for example, here this will be blue one. These two are of the same color, and also these two are of the same color. And if you will repeat the procedure, that to each vertex you will write a triple, that how many blue neighbors it has, how many red and how many yellows. Then this has 0 to 0. This has no blue neighbor, 1 red and 1 yellow. This the same. And here you have 1, 1, 1, 1, 1, 1. And you can see that none of the colors will split into pieces because both yellow vertices have the same triple, both red vertices have the same triple, and the blue vertex, of course, has some triple. So here the next coloring will be the same. So this means that this procedure ended with a stable coloring. And the Weisfeller stabilization is doing the same thing, but for the ordered pairs of vertices. And as I said, that the numbers which could be assigned to such pairs are the numbers of two walks with a prescribed combination of colors. And exactly in these matrices, for example, this entry says that I have two walks such that the first edge is of color 4, second edge is color 1. After that, I have two walks such that the first dart is of color 4, second is of color 3. After that, I have one such that color 5 is followed by color 4, and so on. So this is the combinatorial meaning of the second power, and why we needed to have non-commuting variables, because clearly it is different that I have a yellow dart followed by red dart, and the opposite case that if I have a red dart followed by a yellow one. So this is the meaning behind this process. So now we can formally describe this algorithm. That let us consider an adjacency matrix A. Doesn't matter whether it is directed or undirected, and we can assign to to each entry some non-commuting variable according to the previous rule that which are different, they will obtain different variables, and which are in the same relation at that moment, then they will assign the same. We are counting after that the second power and taking a look what can be distinguished and what not, and we will repeat the same procedure until we will reach a stable matrix. So by the moment when the matrices are non-equivalent. Whenever we reach in 2 consecutive steps equivalent matrices, then we are done, we are finished. So as it was mentioned in the introduction, this now plays a very important role in mainly in computer science, and you can find a lot of papers, a lot of presentations on this, and with starting to use it in many applications. And if we understand how this procedure works, then clearly if we start from a graph, then of course this procedure can distinguish pairs of vertices which are in different distance. If 2 pairs of vertices are in different distance, then clearly at the end of this algorithm, they will be in different relation or will be assigned different colors. So now we will take a look what can be said in connection with distances in graphs and coherent algebras. So just to repeat, the distance between vertices x and y is the length of a shortest path between x and y, and the diameter of a graph is the maximal value of a distance between some vertices in gamma. An interesting family of graphs is called distance transitive graphs, and these graphs have the following property, that whenever I have 2 pairs of vertices, for example xy and uv, which are in the same distance, then there exists an automorphism of the group, or of the graph, sorry, such that it sends the first pair to the second pair in ordered sense. An example for this graph is, for example, the three-dimensional cube. Clearly it is vertex transitive, so for example, if I would like to say, and if I will take vertices 1 and 7, then their distance is 2. So here the distance is 2. And if I will choose another pair of vertices in distance 2, for example 3 and 5, then clearly I can, because of vertex transitivity, map the vertex 1 to vertex 3. So the transitivity says me that I am able to do this. And I'm sorry, this is not 7. This is 2, 4, and 8. And for example, 7 is between 4 and 8. Then after I can map 1 to 3, then I can rotate this cube around the vertex 3 that the vertex 5 will be in this position. So on a cube, it is easy to check that this property is really fulfilled. So maybe it needs, for those who are new with this concept, they will need more time, but this really works. And with the cube, it is easy to check that this is really true. So what is important here is the so-called distance decomposition or the metric decomposition of a graph with respect to some vertex. So if I choose a vertex V, then I can do this decomposition that into set gamma 0, I put the vertex V itself. After that, into set gamma 1, I put all the vertices which are at distance 1 from the vertex V. Into gamma 2, all those vertices which are at distance 2, and so on. And if the graph has diameter d, then I have to consider the last set gamma d. But of course, it can happen that the vertex V has a smaller eccentricity than the diameter. So possibly some of these last sets can be empty for this reason. So now let us consider a regular connected graph gamma, which has valency k, diameter d, and this graph is called distance regular if we have numbers b0 up to b, d minus 1, c1 up to c, d, such that for every pair vu at distance j, so here we have distance j, that means that u is in the set gamma gv, and there are constants such that the number of neighbors of u inside the set gamma j minus 1 v is cj, and in the set gamma j plus 1 v it is bj. So just to think about this, if we have two vertices at distance j, then of course all the neighbors of u are in these three sets, gamma j minus 1, gamma j, and gamma j plus 1. Since this graph is regular, then this is clearly the valency minus number in this set and minus number of this vertex, this set. And this definition says that whenever I choose two vertices in the same distance, then these two numbers doesn't depend on the choice, on the concrete choice of vertices v and u, just on their mutual distance. So for each distance up to diameter, we have such constants. And for the reason that this third number is uniquely determined if BG and the CG do exist, then sometimes we are using not only these parameters which are forming the so-called intersection array of distance regular graph, but we are instead of that using an extended intersection array. So if you think about a bit, then you will quickly realize that in the case if this graph has a diameter 2, then clearly it gives a strongly regular graph. And we will use for displaying the intersection array a diagram which will say that how many vertices do we have in the concrete set gamma, say I? After that, how many edges are going from a concrete vertex to the next, I will say, layer? How many are going back from a concrete vertex? How many are staying in the same set? So to each I can assign this triple, or if I'm considering the first set or the last set, then of course one of the constants are not giving sense because there are no edges going from here. So I can display such a graph using such pictures. Maybe it is better to show a concrete example. So let us take the complete bipartite graph K33. It is here. So if I will make the distance decomposition from, say, this vertex V, then clearly this is gamma 1 and this is gamma 2. So gamma 0 contains one vertex, gamma 1 contains 3, gamma 2 contains 2. Now, from each vertex in gamma 0, there are 3 edges going into the set gamma 1, and no other edges, of course. From gamma 1, if I am taking a vertex, then there is one edge going back to gamma 0. Here, I can also write a loop, but there are no edges inside gamma 1. So in such case, when this is 0, then it can be also deleted. And the remaining 2 edges from any vertex are going to gamma 2. And similarly, I can see that from gamma 2 to gamma 1, from each vertex, there are 3 edges going out. So I can write for this graph the extended intersection array as A0 is 0, A1 is 0, A2 is 0. There are 3 edges going out, no edges coming. After that, 2 edges are going out here, no sense to consider. And so this is the extended intersection array of the K3 tree, and the usual intersection array is this 3, 2 and 1, 3. And the same game can be played, for example, with the icosahedron. It is also a distance regular graph with diameter 3. So the distance decomposition contains 1, 5, 5, and 1 vertices respectively. And you can see how the numbers appear. There is some number missing here. 5 is missing, and so on. Maybe I should also give an example of a graph which is not distance regular. For example, you can take this graph and if you take the distance decomposition, for example, from vertex 1, then you will clearly see that this graph is not distance regular. Sorry. So if I rewrite this, then you can see that in the set gamma 1, the vertex 2, from vertex 2, there is one edge going into the set gamma 1, but from vertex 4, there is no such edge. So this is not distance regular. Though the graph itself is vertex transitive and quite nice, but this doesn't necessarily mean that the regularity condition on the distance is satisfied. But we have plenty of nice graphs which are distance regular. For example, also the dodecahedron, and let me mention the Coxeter graph also. It is a graph which has 28 vertices. The vertices can be divided into 4 sets of vertices of size 7. In 3 of the sets, the vertices are joined into a 7 cycle, and from the remaining set of 7 vertices, we have to add from each vertex 3 edges like this, that from T0 there are edges to B0, A0, C0, also from T3 to B3, C3, and A3. I just didn't write all these edges into the picture because I will get a quite messy picture, so it is, I think, better to write that all these edges are missing here. So this is a nice cubic graph of GERT7. And it is distance regular. For those who are interested in the cage problem, that this is not a cage. Though it is quite small graph, small cubic graph with GERT7, the 3-7 cage has 24 vertices. So just a small remark. And also maybe this is not the same as the Stad-Coxeter graph. So, okay, so we have seen a few examples of distance regular graphs. So now we can ask the question, if I make the distance decomposition of a graph, then of course to each distance graph, that means that if I will in the matrix AJ put ones into the place where the corresponding pair of vertices are at distance j and zeros elsewhere, then of course I will decompose all the possible entries into 0-1 matrices, and we can ask what is the connection between this set of matrices and the property of distance regularity of a graph. So maybe also it would be better to give an example that if I have, for example, the 6th cycle, then the distance matrices are like this. So the 0 distance are just the pairs, just the diagonal pairs. From vertex 1 in distance 1 are the vertices 2 and 6. From the vertex 2, 1 and 3. So you can imagine this is the usual adjacency matrix, which is showing that which edges are present and which not. That this coincides with the distance 1 matrix. At distance 2 from the vertex 1, we have a vertex number 3 and vertex number 5, and the full thing is going cyclically. So from vertex 2, 6 and 4. So this is the distance 2 matrix, and distance 3 matrix is 1 with 4. So here we have 1, 1, 1, 2 with 5, and 3 with 6, and all other entries are zeros. So just by considering the distance decomposition, I can obtain a set of matrices, or set of 0-1 matrices which sum up into the all-1 matrix. And if the starting graph is distance regular, then from the property that the matrix multiplication is in close relation with the number of paths or number of walks, then I can immediately write that if I am multiplying the adjacency matrix with the distance matrix, then it is a linear combination of matrices AI minus 1, AI, and AI plus 1, and the corresponding coefficients are coinciding with the combinatorial meaning of the intersection array. So here I have I1, here I have C I plus 1. Okay, maybe not exactly, but you can obtain these coefficients simply by combinatorial interpretation. And why this family of graphs is interesting from the point of view of coherent algebras, it is because if we start with a regular graph which is connected and it has diameter d, then this graph is distance regular if and only if its coherent closure coincides with the coherent closure of the adjacency matrix. If the distance, or how to say, the coherent algebra generated by the adjacency matrix is the same as the coherent algebra generated by the distance matrices. And maybe just a few words about the proof that from the equation from the previous proposition, one can see that each matrix AY can be written as a polynomial in the matrix, in the adjacency matrix, that is matrix A1, and it is not hard to see that the degree of that polynomial will be precisely I. So if from here you will express I plus 1, then you will clearly see that from this you can obtain a polynomial of degree I. And clearly, these matrices are linearly independent by definition, by direct consequence of the definition. The dimension of the VL closure is at least d plus 1 because we already have d plus 1 linearly independent matrices. And since the graph is regular, then A minus Ki times the all one matrix gives us 0. And the all one matrix can be rewritten as the sum of all these matrices, all these distance matrices. And we already know that these products of matrices can be rewritten into the language of polynomials, and from this equation we obtain that the d plus first power of A can be written as a linear combination of the previous powers. So everything can be written just using matrices A0 up to AD. So this is closed, and it means that it coincides with the VL closure. In the opposite direction, it is much easier to see just by using the previous knowledge. We can see that this is really a linear combination because we now assume that this is a coherent algebra, and by the interpretation of matrices A1 up to AD or A0, we can see that the coefficients in the linear combination will be non-trivial just in the case of matrices A y minus 1, A1, y, A, y plus 1, and that coefficients will give us the intersection numbers, and that will mean that the graph is really distance regular. So the most important corollary of this is that the graph, the regular connected graph with diameter d is distance regular if and only if its WL closure is of dimension d plus 1. So on one hand, we know that the distance, if we will decompose the pairs of vertices in a graph into sets, then of course each pairs which are in different distance will be in different relations, and this is saying us that if all such pairs which are at the same distance are in the same relation, then we have a distance regular graph. Now we can continue by a few observations, but first a terminology that if we have a distance regular graph of diameter d, then the corresponding coherent algebra is a Bose-Messner algebra, because we have undirected graphs, so it is commutative. And to this we can associate an association scheme, and this corresponding association scheme is called metric association scheme. Now, a few properties of intersection arrays. The first one is saying that if you have two consecutive layers, and here it is I minus 1 and gamma I, and these have k I minus 1 vertices, these have ki, then ki minus 1 times bi minus 1 is the same as ki times ci. This is because if you take an arbitrary vertex here in gamma I, then there are ci edges going into gamma I minus 1, and from here there are bi minus 1 edges coming out towards gamma 1. So if you count the number of edges between these two sets, then on one hand you obtain that there are ki minus 1 times bi minus 1, and if you count it from the second part, then it is ki times ci. So this is showing us the validity of the first equation. The second chain of inequalities is a little bit more interesting, but I will need more space, so probably I will immediately erase this one. So the first one was so easy that I think not necessary to have this picture anymore. So let us take a vertex V and at distance 1 vertex X such that on shortest path of length I plus 1 from V to U, this vertex is there. So maybe it will be not a good idea to have here an implication, but such that. And now consider a vertex W, which is at distance I minus 1 from X and from distance 1 from U. Clearly, the distance between V and W is at most I, because here I have paths of length I. On the other hand, since these two vertices V and U are at distance I plus 1, it cannot be less, because otherwise these paths will be shorter than this one. So from this reason, the distance between V and W is exactly Y. That means that I was considering that V is at distance I minus 1 from X and at distance 1 from U. And now I obtain that V is at distance I from V, and of course still it is at distance 1 from U. And this means that gamma I minus 1x intersection with gamma 1 U is less or equal to gamma I V intersection gamma 1 U. And since these cardinalities doesn't depend on the choice of the concrete vertices, so the first one has Ci, cardinality Ci, and the second one has cardinality Ci plus 1. So this means that this chain of inequalities are valid. And similarly, one can show for the intersection numbers B1 up to BD minus 1 that they are forming a non-decreasing sequence. And similarly, as for association scheme, we call a distance regular graph primitive if the corresponding association scheme is primitive. And this happens that in the case when each of the distance graphs are connected. And of course, in other case, we are call such graph an imprimitive graph. And a new thing here is that we call a distance regular graph to be antipodal if the graph corresponding to the distance equal to diameter is disconnected. For example, if you have the cube then vertices which are at distance 3 are this one, I think this one, this one, and so the corresponding distance graph is disconnected. So for example, the three-dimensional cube is antipodal graph, and an important and interesting result here is if we have an imprimitive distance regular graph gamma, then it is bipartite or antipodal. There is no other case that can appear. And if we take a look on what we already know, that we could see that the cube is also bipartite and antipodal. The complete bipartite 3-3 is just a bipartite. And also by careful checking, we can see that the icosahedron and the dodecahedron are antipodal. Coxeter graph is not antipodal, but it is primitive distance regular graph. And I will show you the next definition, because I know that in Novosibirsk, for example, there are a lot of research in coding theory and its relations to algebraic graph theory. So here I am showing the Hamming scheme, which can be obtained like this. Take an n-dimensional cube that is the nth Cartesian product of the sets 0, 1, and you can create relations Rk in such manner that you put a pair of vertices into the class Rk when their coordinates differ in exactly k places. So, for example, the cube can be written with vertices like this. And here I will have 1, 0, 1. That means that I have to join these two. 1, 1, 0. I have to join these. And this is, oh, sorry. This is not correct. Correct will be 1, 1, 0, 1, 1 here, right? Okay, now it looks good. So you can define a three-dimensional cube with this set of vertices, and the relation R1 corresponds exactly to the edges of this graph. R2 will be the distance 2 graph, what can be easily obtained from the picture when the vertices will be in relation exactly when they are differing in 2 coordinates, and the distance 3 graphs, or the relation R3, is obtained by the pairs of vertices which differ in all places. So the obtained structure is a distance regular graph with this extended intersection array, and the corresponding association scheme is called the Hamming scheme over the binary alphabet. So this is an important tool in coding theory. And now let's come back to algebraic graph theory. if we are thinking about the association schemes, then of course we have association schemes of rank 2. That means that we have two relations which are corresponding to the diagonal relation and the rest of the word. So this is not so interesting. This is a trivial association scheme. So the first non-trivial case appears when the rank is 3. So since we are speaking about an association scheme, then the full diagonal relation should be one of the relations. And we have just two possibilities how to complete this into rank 3. If the basic graph is undirected, then this is the case when we have a strongly regular graph. And if it is directed, then clearly the remaining two relations should be mutually transposed, and this is corresponding to doubly regular tournaments. So both these families of graphs are interesting itself. And they can be regarded as a combinatorial approximation of transitive actions. So in similar concept, one can define rank 3 graphs that, starting with a group, if we create the two orbits, and there will be just two orbits, one diagonal, and one will be defining edges, and the remaining will be defined will define the non-edges. Then clearly we are obtaining a rank 3 graph. And if we have a graph with these properties, that if we create its group of automorphisms, and there are just these two orbits, then such a graph is called rank 3 graph. For example, Petersen graph is a rank 3 graph. That means that it is edge transitive and also non-edge transitive. So maybe this is the most frank approach to these graphs, that they are vertex transitive, they are edge transitive, and they are non-edge transitive. So all rank 3 graphs can be described using finite simple groups. So in a sense, if we know all the finite simple groups, then we have complete information about rank 3 graphs. But of course, it can happen that we have a strongly regular graph, but its group of automorphisms is not transitive on the non-edges. So into at least two relations, and this will increase the rank of that graph. And on the other hand, this will also mean that such a graph is non-Schurian, because it cannot be written using two orbits of a group. So this class of graphs gives us more task for investigation, or how to say that, a lot of space for research. So it is interesting to investigate such graphs. So I don't know how many of you were solving the homework from the last lecture. I was giving there the formal definition of strongly regular graphs. So I don't think I have to repeat what a strongly regular gives. I was already using it before. So as the time is slightly pushing, then I will show you two examples which are known, well known. So for example, pentagon is a strongly regular graph because it is regular of valency 2. Each two non-adjacent vertices have one common neighbor. This is the parameter mu. And if the vertices are adjacent, then they have no common neighbor. So the pentagon is a strongly regular graph on 5 vertices with degree 2 and parameter lambda 0 and parameter mu 1. And it is easy to check that this graph is primitive because its complement is also connected. And the Petersen graph is also primitive. It is rank 3 graph because its group of automorphisms act transitively on edges and also on the non-edges. And this family of graphs, strongly regular graphs, is also interesting from the spectral point of view. So one of the tasks for homework was to compute these metrics. So last time we said that there is a close relation between the adjacency algebra and the intersection algebra, and there is anti-isomorphism between them. And since we are now playing with the undirected graphs, then these algebras are commutative, and therefore anti-isomorphism can be replaced by isomorphism. And if you counted this intersection matrix on the homework, then you will understand that the eigenvalues of a strongly regular graph can be computed as eigenvalues of this first intersection matrix. And it is not hard to count the eigenvalues of a 3x3 matrix. So the characteristic polynomial will be like this, and from this it is easy to see that really it has at most 3 distinct eigenvalues. Moreover, with small exception of one family, all these eigenvalues will be integers. So that's another important property of these graphs, that they are forming a quite huge family of integral graphs. And I will conclude this today's lecture with stating that the strongly regular graphs are playing a very important and central role in algebraic graph theory. So I will tell what are the main problems about these graphs. So on the webpage of Professor Brouwer, you can find I think almost all information concerning strongly regular graphs. You will find there the tables of feasible parameters And also, what is the status of that parameter set? That means that there are three possibilities: that it is known that there is such graph on that parameter set, or it is not known whether there is or not, or it is shown that there is no such graph. So the usual goals of researchers are to prove, first to find an example which is realizing that parameter set which is open. After that, we can ask how many such graphs there exist, and also if the parameter set is, I will say, suspicious, then one can try to prove whether there is at all such graph on that parameter set. So prove the existence or non-existence of such graphs with that parameter set. And I will say that now what is open is probably quite hard to decide. I checked 2 or 3 days ago what are the smallest open cases for existence. The smallest open case is on 69 vertices. After that, there are 3 open cases on 85 vertices. And also there is on 88 vertices. Besides that, also there are of some interest the strongly regular graphs which are triangle free. That means if a strongly regular graph is triangle free, then the parameter lambda cannot be non-zero, because if lambda is at least 1, then you have immediately a triangle. So triangle-free strongly regular graphs are precisely those which have parameter lambda equals to 0. The smallest open case is on 162 vertices, and the existence of that graph is closely related to the existence of a mixed Moore graph on 486 vertices. Moore graphs in undirected case are such that if you have 2 vertices u and v, then there is precisely one path of length at most 2. So if these 2 vertices are joined by an edge, then there is no path of length 2 in between them. And if they are not joined by an edge, then there is precisely one path of length 2 from u to v. And the same in similar manner, the mixed Moore graphs are defined. So these problems are belonging to the extremal graph theory. And I think in that direction, the most famous open problem is the existence of the Moore graph of valency 57. So this, if you prove or disprove the existence of such a graph of with these parameters, then you will become probably famous. So there are lots of interesting open problems in this area. So you are welcome to work in that. It would be nice to see new results. For example, this February, Oleg Gritsenko found a strongly regular graph with parameter sets with parameters 65, 32, 15, 16, which was previously unknown. So it was quite surprising that this parameter set was open for a long time, and now recently, by a clever construction, somebody found a graph. So really, new ideas can bring new results. So I think everybody can do something in this area. So I think that's all for today from my side. So thank you very much for your attention.
Thank you very much for this very nice and detailed lecture on coherent closure with finishing on open problems on strongly regular graphs. That is very important to know what we don't know right now. Okay, are there any questions to Štefan?
I have just one question.
Yeah, sure, please.
You mentioned that the existence of Moore graph with valency 57 is still undecided, but I think there is on arXiv posted a paper by Professor Machniev, I think, which says that, I think the paper is in Russian, but abstract is written in English, and it is written that he proved the non-existence of this strongly regular graph on Moore graph. I don't know if the paper is already published somewhere, but it is on arXiv.
Yes, I know about that paper, but if I have correct information that there are people who are saying that there are some inaccuracies. So at this moment, it is still not approved that what he is writing is really
okay.
true.
I didn't know that. Okay.
Can I make a comment?
Who is the author?
Can I make a comment? As a member of research group where Machniev is working.
Okay, please, Natalia.
As I know, now Alexander Machniev is working on some revisions of his proof, and if all the proofs will be correct, he will write a paper in English.
Oh, okay, great.
But now he is working on some inaccuracies, but I haven't listened that this process is already finished. But I think after some time possible he will finish.
Great. Thank you. I didn't know that. Okay, thank you.
Okay, Natalia, please be in touch with us on this matter. So
Sure.
you see, so many people are interested in knowing about existence and non-existence of this graph.
I think that if Professor Machniev will finish his paper in English, he will ensure put it to arXiv in English version to make it possible to read for all body.
Good, very nice, yeah.
Thank you.
Okay, any other questions to Štefan? Well, if not, then let us thank again Štefan for this very nice lecture containing a lot of useful informations, and actually, well, I like this style because you explain us all details, and that is very important. Thank you very much. Well, okay, the next
Thank
lecture.
you, Stefan. Thank you.
Yeah, thank you. Next lecture will be given in 2 weeks, and it will be on some small non-Schurian association scheme and coherent configuration. So Štefan will continue this topic, and I'm sure that we will get a lot of new interesting facts on this matter. So thank you very much. And now, if there is no any other questions, then let us stop this lecture, this meeting today. See you in 2 weeks.
See you. Bye bye. Thank you.
Bye bye. Bye bye. Okay,
Bye-bye.
thank you.
Bye-bye.
Bye.
Bye-bye.
Many thanks.
Yeah.